right, everyone. I am here with Rose Yu. Rose is an assistant professor at UC San Diego. Rose, welcome to the TWiML AI podcast.
Thank you.
I'd love to have you start by sharing a little bit about your background and how you came to work in machine learning.
Sure. So I'm currently assistant professor at UC San Diego Computer Science and Hollywood Data Science Institute. So I did my PhD at USC Computer Science, and then I finished my postdoc training at Caltech, Computer Science and Mathematics. So my machine learning journey started way earlier when I was an undergraduate, when I participated in an undergraduate research project and was able to publish a paper at the AAAI, which is one of the top AI conferences almost 10 years ago. And that started my journey in machine learning. And throughout my journey, I got a lot of mentorship and help from my advisors, postdoc advisors, my collaborators and students. And that's how I landed here.
Nice, nice. Tell us about your research interests. What do you focus on from a research perspective?
Absolutely. So my research focused on advancing machine learning algorithms and methods for analyzing large-scale time series and spatial-temporal data.
Mm-hmm.
So specifically, we develop research in deep learning, tensor methods, non-convex optimization to understand dynamical systems. We apply these methods to solve challenging problems in climate science, in transportation, and many other physical science areas. So compare with traditional applications in machine learning, such as image data or text data, spatial-temporal data has their own unique challenges, and oftentimes they are governed by certain physical processes underneath. So the reason research thrust of our lab is called physics-guided AI, where we aim to integrate first principle methods from physics into data-driven machine learning models, such that they are more accurate, more physically consistent, and more trustworthy.
Oh, nice. So maybe we can start by having you talk about some of the use case areas that you apply your research to, just to give us some context.
Sure. So as an example, in climate science, climate models are often used to understand the evolution of atmospheric dynamics. However, climate models at higher scale, space, and time resolution are extremely time-consuming to simulate. Usually, running a climate model at full scale across the globe takes a couple months. So this is already too late when we want to understand the change of the climate, the weather, or to make predictions of what's going to happen in the atmospheric environment. So one of the research projects was published in KDD 2020 and iClear 2021 is about developing deep learning models that can speed up this process. Essentially, we want to build deep learning models that can emulate the evolution of climate simulations. And these climate simulations are typically governed by partial differential equations that describes underlying physical processes. So the main challenge is if we just use a vanilla deep learning model, they will not be able to capture the physical characteristics of the underlying phenomenon. So in our example, we use the hybrid models to borrow ideas from physical sciences, such as integrating ideas about computational fluid dynamics, or integrating ideas about symmetry into deep learning. So in this way, our deep learning models can not only emulate the evolution of, for example, turbulence, which is a very common phenomenon in climate, it will also be able to predict values that are physically meaningful. So as an example, we can measure when we try to predict the turbulence evolution, which is very common in clouds evolution in ocean current evolution. So
And when
when
you
we
say
want
evolution, you're primarily referring to just the way it develops over time, and that this is where kind of the time series element comes in?
exactly. So they're basically values that are changing over time. So
Mhm,
mathematically, it's called dynamical system. And
mhm.
when we try to develop, basically describe the change in these values, and that's what I meant by evolution.
Yep. Okay.
Um, so when in the one about KDD papers, what we showed is that if you just predict, for instance, the evolution of turbulence velocity, right? You're essentially predicting a video right into the future, given the past frames of video. However, if you just use a video prediction methods that are developed out of computer vision community, then the predicted values of this video are not able to capture the correct energy spectrum of the underlying turbulence. And in turbulence community, this kind of energy cascade or energy spectrum is critical to describe the underlying physical characteristics of the system. Whereas if we use our hybrid model, where we combine ideas from physical modeling and deep learning, our model is able to generate much more physically meaningful predictions, and our predicted energy spectrum actually matches well with the ground truth.
And so just so I understand the setup here, is the key distinction that you're making between a model that's based on video and a model that's maybe a higher dimensional model, or are you using video in both cases, but in one case you're not using the physical knowledge that you have, and in the other case you're incorporating that physical knowledge?
Yeah, it's a second case where
Okay,
both models are fed with the same information.
got it.
Whereas in the natural video, because it's very complicated, we have many objects interacting with each other. It's very difficult to describe them with certain equations or certain governing laws, right? But
Mhm,
in turbulence, the nice thing is that we know the underlying governing equation, and we have a lot of techniques from computational fluid dynamic community that we can exploit. So by exploiting this type of knowledge, we can improve our predictions by significant amount.
mhm. And so you mentioned spatiotemporal data. It sounds I'm inferring from that that the differential equations that you're using, or the partial differential equations that you're using, are relative to both space and time.
Correct.
And so, how do you incorporate in those that physical knowledge or those partial differential equations?
Yeah, great question. So there are multiple ways, right? So in the KDD paper, what we basically leverage is that, the multi-scale modeling. We actually did not use the equation themselves, but rather we're looking at how people usually approximate these solutions of the equations. What we found is that there are basically convolutional operators that are computed over space and time. And this in CFD community was called the spatial averaging or temporal averaging, right? And more, I guess the acronyms are, RANS LES coupling. And
Say
what we
that again.
found, the RANS LES coupling.
Okay.
RANS is the Reynolds averaging. Right? L is
Okay.
large eddy simulation.
Okay.
And they're essentially calculating the space and time average using convolutional operator. So what we did is that, instead of using deep learning to approximate the partial differential equations themselves, we're going to approximate the convolutional operator by replacing these traditional design operators with trainable neural networks, which boils down to convolutional neural nets. So then we have separate convolutional modules to capture different scales of turbulence. And by doing so, we can model the multi-scale behavior in the turbulence and generate much better prediction. So that's one of the ways we can exploit the underlying physics. The iClear paper, which was recently published, is about looking at the symmetries in the partial differential equation, right? Because you know if we think about partial differential equations, there are a lot of symmetries, and by symmetry, what I mean is if I have a solution that is a solution of the partial differential equation, and I can apply certain transformations to this equation by, for example, shifting by certain amount or rotating by certain amount.
Hmm.
or scale it up by a certain amount. And this kind of transformation will change the equation themselves, but they will not change the solution by itself. So that's a symmetry in the solution of the PDEs. And what we found out is that, if we can incorporate the symmetries into our deep learning model, we can also capture the underlying physics, right? Because there is a Noether theorem that links the conservation laws with symmetry, essentially saying that for every symmetry, there is a conservation law. The time translation symmetry will correspond to energy conservation.
Okay.
So if we can incorporate this type of symmetries into deep learning, we naturally satisfy conservation laws, which are very important in physical modeling, right? And this idea
And
is not.
is the symmetry um, across properties, meaning between the time and the energy properties of the system, or is it within the time domain or within the energy domain you're exploiting symmetries?
Oh, it's multiple. So it depends on what type of symmetry groups that you're considering, right? So, for example, if you're considering the symmetry on along the time translation, that is only on time. But if you consider for the Galilean transformation, which is basically about space and time, right? Then the scaling is about a different transformation on the input. And this idea of exploiting symmetry in deep learning is not new. So the
Mhm.
reason, for example, convolutional neural networks are so successful in modeling image data is that it leveraged translation symmetry in the spatial domain. Similarly, the reason why RNNs are very powerful in modeling sequence data is that it has built-in time translation symmetry.
Mhm.
Right, and then graph neural networks are very powerful in modeling graph data or set data because it has, intrinsic permutation symmetry. So this idea of incorporating symmetry in deep learning is not new, but what we did is to generalize this idea to dynamical systems, to model space and time data that is basically governed by partial differential equations. And we use this model to predict the evolution of turbulence, the future states of ocean currents, or even forecast the future trajectories of autonomous vehicles.
Got it. And so, how exactly did you incorporate the symmetry properties into the deep learning models that you built?
Yeah, so that's actually the whole paper is about. And so, the one idea is basically, right, think about how convolutional neural networks is able to incorporate translation symmetry, and
Hmm.
that's through weight sharing. And the same, basically within the same filter, there are different weights, but across different filter, they use the exact same weights. And that basically allows us to incorporate translation symmetry in convolutes. Right? And we can apply the same idea to other kind of symmetry groups. For example, if we wanted to incorporate scaling symmetry, now we basically need to design the filters in the convolutional architecture such that they're shared within different scales. And of course, you have to deal with different kind of coordinates in the autonomous vehicle paper or the echo paper, equivariant continuous convolution. What we did is to work in the polar coordinates instead of the Euclidean space, right? And then we can model basically the scaling in terms of angle and the radius, and then we can share weights along basically different like radius, but then have different weights with different angles.
Hmm. And so, in the case of is the paper that you're referring to, is it are there separate papers for each of these use cases that is incorporating the symmetry information, or is the paper primarily about methods to incorporate the symmetry into the dynamical models?
That's a nice question. So it's a bit of both, right? Because
Okay.
we often, we conduct a use-inspired research, where we often develop method inspired by certain use cases.
Hmm.
So we have, two papers that I clear, which about incorporating symmetry, and the first one is about incorporating different symmetry groups into deep sequence models for forecasting videos, essentially for turbulence velocity fields and for ocean currents,
Okay.
right? And obviously these symmetries are derived from PDEs and the Navier-Stokes equations, but we would imagine these methods that we developed are generically applicable to similar type of data, right? The other paper that we published about equivariance continuous convolution is about point cloud data, right? So we
Mhm.
have point clouds collected about from autonomous vehicles using LiDAR, right? And we can basically work in a polar coordinate framework. And then we design equivariance continuous convolution, which essentially allows us to model rotation symmetry and scale symmetry in this point cloud data. And we basically tested our method for the autonomous vehicle prediction tasks and as well as the pedestrian trajectory prediction tests. But we also imagine that this method will probably be useful for other kind of point cloud data.
Okay. I think your previous answer anticipated a question that I was starting to have, and that was, when you talk about these symmetries, there are symmetries that we know kind of exists based on the properties of these systems of PDEs, and then but there's a separate type of symmetry that kind of emerges from the data itself, and you're developing methods to kind of handle both of them. Are they totally separate use cases, or are they kind of ultimately linked by the data that the PDEs create?
That's very great observation. So actually, there are basically multiple type of symmetry that can exist, as you alluded to. One is basically derived from partial differential equations, right?
Hmm.
Then we can analytically basically write down what are the
Right.
symmetries that this set of equations satisfy. And that's what's used in the ICLR paper about incorporating symmetries into deep dynamics models. But what we showed is that even though, right, sometimes we have data where we have no idea what are the actual equations that governs it. For example,
Okay.
ocean currents. We only know approximately that maybe Navier-Stokes equations are the governing equation of ocean currents, but there are because the underlying processes are so complicated, and we cannot write out all the possible symmetries of this data.
Hmm.
But the model still performs well in this case. That just means even with approximate symmetry or some very, vague idea of why it can help, it will help in terms of prediction, right? So that's the first part. And the data symmetry is about sometimes we have some intuition of the symmetry in the system that we want to model. For instance, in the autonomous vehicles, we cannot derive the equations that
Hmm.
capture the motion of autonomous vehicle because it's so complicated,
Hmm.
right? But we have some intuition of what kind of symmetry can exist in driving, right? For instance, when we drive in the North America, right, and we wanted to turn right, and
Hmm.
we automatically know how to turn right, and
Hmm.
then suddenly, let's say if we move to south hemisphere, right, then we drive in Australia, for example, and we still wanted to turn right, but our brain can automatically adjust this change of reference and still be able to recognize that we can turn right,
Hmm.
even though we're in a completely different reference point, right? So then this kind of intrinsic or implicit symmetry is built into our reasoning framework. And then we can incorporate this kind of symmetry also in our model to improve predictions.
Okay. You mentioned that we don't have the equations to model ocean currents, and this is maybe a bit of a digression, but that's somehow surprising to me. Just thinking about, like, we know a lot about, for example, modeling air currents and weather. We do a pretty good job at that. I would have thought that ocean currents would be pretty similar, and we have all those equations, but it sounds like that's not the case.
Well, we work closely with climate scientists, and What
Hmm.
they told me that is the climate models are not as good as you thought.
Okay.
And that's why there are so many great challenges that we need to work on.
Got it. Got it. Got it. Um, and so you mentioned you mentioned convolutional neural nets. You mentioned graphs. You mentioned RNNs. It sounds like your work is primarily focused on using convolution operators and translational symmetry, or are you working with these other kinds of networks as well?
No, we actually develop our own network, right? That's what I'm trying to say. Like, as an example of how
Okay.
symmetry was incorporated into deep learning to improve prediction, and CNNs and RNNs are exactly these examples, but these are only focused on translation symmetry, right? And for
Hmm.
general symmetry, such as, rotation symmetry, scaling symmetry, and even continuous symmetries in Lie groups, there are no neural networks that can do that. So that's basically our contribution. We are designing new type of neural networks that can do that, and
Got it. Got it.
obviously build on other people's work.
Got it. I thought I had heard that you'd somehow mapped these types of translation onto the convolution operators. But
Yeah, so the one of them, for example, is called convolution, but it's not the regular convolution.
okay,
It's built on the work of Kondo and Trivedi, right, and many others, work about group convolution, right? So it's a
okay,
different type of mathematical operator.
got it. And so then, can you talk a little bit about how you get from the mathematical representations of convolution or of symmetry or uh, translation that you care about to the network architectures that you developed?
So yeah, basically, once we came up with the right group convolution, right, which
Hmm.
is a type of, mathematical operator, and we can implement them in, neural networks through either tensor construction or matrix multiplication. Right. Once we do that, we basically define our forward path using the deep learning framework such as PyTorch, and then we can just, build it up as a module in a deep learning, neural network.
Got
The
it.
zoo of neural networks.
Okay. And you mentioned tensor methods as being one of the tools that you use. Can you talk a little bit more about that?
Sure. So the tensor methods actually came out of my PhD work. Right? My PhD work was about, developing tensor methods to understand spatial-temporal data, because tensor methods they're not deep methods, they're shallow methods, right? But the nice thing is that they provide much more interpretable predictions. So we can understand, when we look at the prediction of a deep learning model, sometimes we're puzzled like why this model is making this kind of prediction. Whereas tensor model, the shadow model, it has multilinear structure between the input and output, and it's easier for us to diagnose this model and understand what is contributing to the prediction of the model. So another thing about tensor model is that it generalized the matrix methods, which usually matrix methods models the pairwise relationships. Think about the Netflix challenge in movie reviews, where using matrix compilation, you can model the pairwise relationship between user and movies. But a lot of times when we model, say, spatial temporal data, there are higher order correlations, right? There are
Mhm.
correlations among different locations, and there are correlations among different timestamps, and there are also correlations among different features or variables. So matrix methods are insufficient to model this kind of higher order correlation, and that's where tensor methods shine. In this regime, it allows us to model, triplets information or even higher order correlation, but at the same time generate interpretable models to help us understand what's going on, right? And I guess another kind of relatively exciting direction is that deep learning is mostly about non-convex optimization. So unfortunately, a lot of the optimization techniques and analysis were developed for convex regime. So tensor methods are non-convex, and it provides us with a nice platform to study this group of non-convex optimization problem, and hopefully the insights that we derive from understanding tensor methods can be generalized to understanding deep learning.
Nice, nice. You've also got a paper focused on looking at the uncertainty within these deep spatiotemporal models. Is that built on the work that we've been discussing thus far, or are they
Um,
separate models?
So they are basically related, but they are not
Hmm.
the physics-based model yet. So this is just the first step for us to look at the risk assessment and uncertainty quantification. Actually, in terms of physics-guided AI, the model that we use for this paper is a slightly different technique. It basically learns the residuals between the physics-based model and the ground truth. So you asked about how can you incorporate physics into deep learning model, and this is the third way, right? Because we
Hmm.
talked about learning the convolutional operators, we talked about incorporating symmetries, and the third way that we did is to learn the residuals, to learn the correction term between the ground truth data and the physics simulators.
Hmm.
Um, so in this paper, which is recently published in IKDD, is about forecasting COVID-19 or forecasting air quality, where we have very sparse data set. Right, in these regions, we cannot have a million of data points to train, and using a deep learning model obviously will not perform well because it's in a small data regime.
Hmm.
So what we did is to incorporate, physics models as a prior and learn the correction terms between the ground truth and the physics-based model. So in that way, we can use the physics model as a starting point, and we don't need that much data to train. Um, and in these regimes, obviously, because we have fewer data points, and it's important to characterize not only the prediction themselves, but also the confidence interval. So imagine if we want to forecast the number of infected cases in the next 4 weeks. It's not enough just to say the next 4 weeks infected cases will be, X amount. But we also need to say the next 4 weeks infected cases will be X amount with 90% confidence. So that's what I mean by uncertainty quantification, and it's extremely important in spatial-temporal forecasting in physics-based model as well, right? It gives us a tool to assess the risk that attached to it. So what we did in this paper is to investigate in a benchmark study what type of uncertainty quantification techniques that we can use in the context of deep learning.
Okay. And what did you find there? Did you kind of looked at the landscape, but did you find some methods that you thought would be interesting for the kinds of problems that you care most about?
Yeah, exactly. So usually, right, when people think about uncertainty quantification for deep learning, the to-go method is Bayesian neural networks.
Hmm.
And usually, Bayesian neural networks, there are different techniques such as Monte Carlo dropout, which is approximate Bayesian inference method, and there is also more exact Bayesian inference method based on Markov chain Monte Carlo. So what we did in this paper is to look at two group of methods: the frequentist UQ methods and the Bayesian UQ method. So what we found is that within the frequentist UQ methods, there are classic techniques based on bootstrap or based on interval scores, right? And they are actually quite competitive in generating the confidence interval, but then they often provide a very wide confidence interval, which means they have good coverage of the forecast, but they may not have very high confidence.
Hmm.
Whereas, in the Bayesian regime, we looked at, the stochastic gradient MCMC, which is a type of Monte Carlo method, and we also looked at Monte Carlo dropout, which is the approximate Bayesian inference method for UQ. And what we found is that, the Markov chain Monte Carlo methods, they give very good confidence intervals, and they also have a good coverage. However, it takes a long time to train because we have to run the deep learning methods multiple times and to collect the samples. So it's a very time consuming process. And then Monte Carlo dropout provides good coverage, but it doesn't give the good intervals in terms of the uncertainty quantification, right? So
Sounds
the
like you need to
conclusion.
pick your poison.
Exactly. So then the conclusion is that there is no winner takes all situation in
Yeah.
uncertainty quantification. It's really about a balance in computation, in sample complexity, in the coverage of the prediction and the accuracy. So therefore, we provide a recipe for the practitioners in our paper, right? And you can just look at the recipe and deciding on what method you want to use for uncertainty quantification.
Kind of like a flow chart.
Yeah.
Got it. Awesome. Awesome. So maybe we can wrap up by having you share a little bit about future directions and what you're seeing as being exciting in the space and where you want to take your research.
Sure, absolutely. So, as I mentioned, the physics-based AI is just at its beginning, right?
Hmm.
The idea of incorporating, domain knowledge and physical laws into machine learning model is a really exciting direction. And right now, we have been only focused on, just generating predictions or emulating the models. The future of this direction will about decision making as well. How can we leverage, existing physical models combined with data to make better decisions, right? And that will involve, new techniques such as the Bayesian optimization, reinforcement learning, and even techniques from mechanism design and economics, right? These are the new kind of direction that we want to push for. And
Hmm.
again, the key there is to not only blindly trust the data and develop black box models, but rather to understand the underlying governing process of the data and to exploit the known domain knowledge in this data in physical laws, in conservation laws, and all kinds of principles that we have to build better models, right? And in this way, we can, really advance. I guess one of the passion is to use AI to advance scientific development and engineering, right?
Hmm.
So if we wanted to really do that, we really need to develop models that can understand the physics, it can understand the science behind it, and can be trustworthy for the domain scientist to use them.
Awesome. Awesome. Well, Rose, thanks so much for taking the time to share a bit
Thank
about what
you.
you're working on. It's great to learn a bit about your research.
Thank you so much for this interview.
Thank you.